Every complex structure in mathematics can be dismantled into irreducible building blocks. Before we can manipulate heavy algebraic equations, we have to understand the basic arithmetic DNA that holds them together. This factor tree illustrates the principle. We take a familiar integer, 90, and break it down until it can't be divided any further, leaving us with its prime index form, 2 times 3 squared times 5. By placing two factored numbers side by side, we can extract the highest common factor and the lowest common multiple. Finding the highest common factor requires isolating the lowest power of the prime numbers shared between terms. For the lowest common multiple, we group the highest power of every distinct factor present. Extracting prime numbers from integers is the baseline, but this arithmetic warm-up is only a preparation for the level of manipulation required in advanced algebra. This teacher's note from the ZIMSEC syllabus identifies a specific threshold. It notes that mastering advanced algebraic fractions is what separates students who pass the exam from those who merely attempt it. This problem represents that threshold. To solve it, we have to find commonalities across multiple quadratic expressions simultaneously. Without the visible landmarks of prime numbers, these variables and squares can feel disconnected from the basic rules of arithmetic. The challenge is seeing how the logic of factors and multiples still applies when the numbers are replaced by variables. Variables do not introduce a new set of rules. They are placeholders, following the same structural logic as the numbers they represent. This diagram shows two algebraic terms deconstructed into raw individual factors. 6xy is 6 times x times y. 18x squared is 3 times 6 times x times x. By identifying shared factors, the 6 and a single x, we arrive at a highest common factor of 6x. These variables submit to the same logic as prime numbers. The underlying principle of factorization remains constant as the terms become more abstract. This specific practice set moves to a higher level of complexity, finding the lowest common multiple of full polynomial expressions. As shown in this example, the first step is to dismantle these quadratics. The difference of two squares allows us to split x squared minus 4 into the factors x plus 2 and x minus 2. We do the same for the trinomial. Finding numbers that multiply to -6 and add to 1 splits the expression into x minus 2 and x plus 3. Once in parentheses, the entire expression functions as a single unit, just like a prime number. We can now apply our factor rules to these brackets. We select the shared block, x minus 2, for the highest common factor, and group every distinct block together to form the lowest common multiple. A quadratic trinomial is simply a standard factor problem where the prime building blocks are hidden inside brackets. We can now return to the algebraic fraction that appeared unsolvable in Act 1. We substitute the raw polynomials in the numerator and denominator with the factored brackets we just uncovered. With the true factors exposed, we simplify the expression by canceling matching blocks from the top and bottom. The x plus 2 units cancel out. The x minus 3 units cancel out. The huge fraction collapses into a final algebraic line, x minus 3 over x plus 3. Mastering factorization allows us to dismantle high-level expressions using the same tools used for basic integers. The complexity changes, but the logic remains constant.